Let me try again. I was muted. Well, it looks like we can start. Welcome back, everyone. We're now on week number 12. So once this week is done, we're crossing over the 75th percent mark for the entire semester. Congratulations on getting through it so far. And with what we have going on this week, it's kind of an ordinary week so far. We'll be finishing off our chapter on statistical reasoning and then moving into the next chapter on exponential growth, exponential decay. Aside from that, the other major announcement is we have our third exam coming up. This one's official date will be Monday, April 20, and we're going to pretty much just redo the same pattern of attack that we did for exams 1, exams 2, which means on Friday of this week that we're on currently, after I get caught up on all the grading, I'm going to turn over to posting the exact exam coverage for what will be on the third exam and the sample exam questions, just like we did on the other exams. Also, on Thursday of week number 13, just like for exam 1 and 2, we'll hold a review day as well. Well, any questions at all, folks, to start us out today? Okay, well, let's get started. We're finishing off our chapter 5 on statistics, and it's been quite a journey. This took more time out of the schedule than I originally anticipated when planning for the course. But there's always a lot of stuff to say when it comes to statistics, so I'm glad we took our time with it. So we just have a few more examples to work through in the correlation and causation section. And just for a quick review of what we were doing, a quick recap, we were looking to determine whether data were correlated, and if they're correlated, if the correlation is going to be positive or negative. A graph like this one would mean that there's no correlation whatsoever between the variables. And that's why we said in the reading, or excuse me, in the conclusion here for part B, that arm span, this horizontal quantitative variable, has no bearing on visual reaction time, the vertical quantitative variable, whatsoever. As one changes, the visual reaction time changes as well, but randomly. It don't have any particular direction to the data. So we'll say that there's going to be a positive direction if both variables, not as a rule, absolutely increase together, but tend to. As one variable goes up, the other variable, more likely than not, is also going up. It means the correlation is positive. And if two variables change in the opposite direction, the horizontal one increasing, but the vertical one decreasing, we'll say that's a picture of negative correlation. So we picked up negative correlation on this picture. As the resting heart rate goes up, the overall physical fitness, VO2 max, tends to go down, not as a firm rule. There's some exceptional cases, some outliers in the data, but overall, we see that there is a downward pattern. So that's our recap between these three big definitions here so far. Any questions at all before we get started on our current example? Okay, another thing that was really hard to kind of assess in these graphs is if there's a correlation, you also want to say how strong that relationship might be. We said that this one was weak because a strong relationship means that the points are going to be closer to each other on a line. If they fall exactly on the line, we'd call that perfect correlation. But here there's a good amount of scatter. Here we didn't have to assess the strength whatsoever because there is no correlation. And if there isn't correlation between the variables, we don't need to say how strong it is. There's just none whatsoever. But on our next graph, this one down below here the dots are pretty tightly packed. So when we go to describe this relationship, we'll probably say it's a strong relationship. So here's our new context. We can kind of see what's going on just at a glance from the graph itself, really. This is sunflower growth, stem diameter versus plant height. So the stem diameter in millimeters is this axis, the horizontal one. The total height of the sunflower in centimeters is the vertical axis going this way. And, well, the context is kind of huge on this one. Really, this is the major part of the context. But when I was writing this problem, I realized I didn't know what an agricultural extension office is. So we defined an agricultural extension office here But then there's even more to that. So here's where the problem really starts. It says, to start off the context, a land-grant university is an institution of higher education in the United States designated by its state to receive the benefits of the Morrill Acts of 1862 and 1890. So the idea was to make higher education accessible to the working class, focus on practical everyday sciences, and every single state in the United States has a institution designated in this way. Every state has a land-grant university. For Idaho, it's not ISU. It turns out it's the University of Idaho up in Moscow. So that's that last part right there. Once you have a land-grant university, there's agricultural extension offices that go along with it. So we're told next in the context, an agricultural extension office is a local center connected to the state's land-grant university. So Moscow, University of Idaho for our land-grant university. Its purpose is to take the scientific research from, say, University of Idaho, share it directly with the public in a practical, usable format. So there's a little bit more about that. The system was started by a different act in 1914. And so that's what the Agricultural Extension Office is all about in this problem. Idaho actually does grow sunflowers, so even though these data are made up, this is a pretty realistic problem in terms of the context and the information we see here. So back to where these data actually came from, an Agricultural Extension Office is studying the structural growth patterns of that particular sunflower. There's a scientific name, I'm not going to attempt to pronounce it, to better understand the crop resilience against high winds, which is a big problem with sunflowers. They can blow over very easily. So the researchers randomly selected 30 fully mature sunflowers from a test plot. For each plant, the researchers measured the stem diameter at the base of the plant, and it says they are using calipers to make that measurement. So right at ground level, they found out how wide its trunk was, essentially. Next, they measured the total plant height in centimeters from the soil line to the top of the flower head. So that's the idea behind these data. And we have this pretty decent pattern. There's a pretty strong looking correlation between stem diameter, total height, because if we were to draw a line through these data, it would look about like this. The line isn't perfect. We're not trying to connect the dots, but the dots are all pretty much randomly above and below, very close to a line that we might try to draw through the data. So as far as the strength goes on this one, looks like it's pretty strong in correlation. But any volunteers for what the direction should be? Is this positive correlation or negative correlation?
Positive correlation?
Yeah, absolutely. As the stem diameter, the trunk right at the ground level, gets higher and higher, well, the plant is getting higher and higher itself. That's something we would expect to see from plants, sunflowers ordinarily in nature, or even just say trees, for example. So just like you said, because the pattern is going up, we'll say that there is a positive correlation. The points are very close to each other, so we can say there's a positive correlation that is strong. So that's the first part down. Any questions so far about the context or part A? Okay, there's a little bit more going on with all these problems. We're looking not just at correlation, but causation is part of this, our work on this section as well. And so we were thinking about causation when we were in this portion right here. Maybe let's just screenshot this down for the moment. Whenever we do see a correlation, we wonder, what are the explanation for the correlation that we see? There could be a coincidence, like we mentioned before. It's possible if we take a random sample of 10 observations, they might fall into a pattern just by a coincidence alone. That could have been what happened in example 1, for example. The sample size is a little bit larger here. This is 30 mature sunflowers, so 30 dots plotted. So having a coincidence like that with a larger sample size is much more rare. So another possible reason for the correlation is they might be directly influenced by some common underlying cause. And that might be the case here, but it could just be that one variable is correlated with the other by cause and effect. And that could be the case on this one. It could be just the case that the higher stem diameter allows for and causes a higher total height on this particular sunflower. There's probably more variables that are important, like the soil nutrition, how much wind there is going to be in that region, and so on. But there might be a bona fide causal relationship between these two variables that we see here. But aside from thinking about correlation and causation, the next thing we want to say is just what conclusion can be drawn from the scatter plot. And there's really not too much you have to say. It's kind of formulaic in a certain sense. Once we say there's a positive correlation, then we can just say focus on, first, the horizontal variable. We can now say as the stem diameter increases, so increase in that variable, for positive correlation, we should see an increase in the total height. So we can say next, the total height of the sunflower tends to increase as well. So that's our kind of generic conclusion that we would give for a plot like this one. Just relate the two variables together, mention the direction, whether it's going up or going down, pretty much going back to what you said in part A. And if there's no correlation whatsoever, like in example 2, then we'll just say one variable has nothing to do with the other. Or the way it was phrased from class last time, one variable has no bearing on the other. Well, we'll take a look into another example just to think a bit more about correlation and direction, and then another scatter plot to finish out this unit. Any last questions or comments, folks, after getting through this one? Okay, for me, in this unit, I would say these are my favorite kind of questions because it's all pretty visual. You have something to look at, something to think about. You can draw a line through the data to assess how strong the correlation is. But that's what makes the next kind of examples that you'll see also in my lab just a little bit more challenging because there's almost no context, just a one quick sentence, and there's no visual whatsoever for us to do any kind of assessment. Yet we'll still do the best we can in both part A, part B. It says, for the following pairs of variables, state the units that might be used to measure each variable. That's us convincing ourselves that they're really quantitative variables. These are quantitative variables. You can fit them in a scatter plot and talk about correlation, but also means there's got to be a unit, like millimeters here, centimeters here, a unit of some kind. So we're going to say what the unit might be to measure each variable, then state whether you believe they are correlated. If they are correlated, state whether the correlation is going to be positive, like in the last example, or negative, like in example 1. Challenging here thing is after we determine whether we think they're positive or negative correlated, we have to explain our reasoning as well to support why we chose that direction. So here's two just random scenarios. Looking first at part A, we have two variables, years of professional work experience, and the second variable is annual salary. So first thing we'll do is just put units on both. So for the first one, we can say that years I'll just abbreviate this one to years of work experience. Well, we have to say what the variable would be for this, and it kind of says what it is, right? Let's measure this in years. So for the variable work experience, the unit is years. It just has to be any time unit. If you said months, I mean, that's acceptable as well. It's just that work experience tends to be in the years. So kind of a strange problem. Years is part of the answer on this one for the unit. And for the next one, annual salary, the unit is, well, it's a money unit. So for thinking USA, we could say dollars. For thinking Canada, then it's Canadian dollars and so on. So if we're worried about the context, you could just say any monetary unit. Let's suppose this is in USA. We'll say the unit is dollars. Well, we have two variables down, units on both of them now. Now we have to decide, is professional work experience correlated with annual salary? And if it is correlated, would that correlation be positive or negative? Any volunteers for the assessment on this one?
Are we just making assumptions that yes, probably the annual salary goes up with the amount of experience you have?
Pretty much that's it, yeah. And it is a big assumption, right? Because
Yeah.
if you, for the wrong company, your work experience and salary could be flat. You could work year after year at certain companies, never see a raise. But we would think of that as just one dot if we had a whole scatter plot. So imagine if we had a scatter plot like this, and maybe one dot where we have 50 years of experience, but the salary is flat at your starting pay. But that's just going to be one dot on the scatter plot. So we're imagining, but what about other companies with maybe a kind of a bright outlook? We might say, well, most companies are going to give you a raise after years of experience. Maybe after accumulating experience, you might change jobs and your salary could go up as you change jobs into maybe a different part of your field or a promotion from within the company and so on. So if that's the case, would you all say that that's positive or negative correlation?
Positive.
Yeah. And again, it's a tough problem to assess, right? That's what makes this one tricky is there's no scatter plot that says we randomly assessed 150 companies in USA, and here is the work experience for the average employee in the company on one axis, and the annual salary for the average person in the company on another axis. We're missing all of that context. So we have to put in a lot of this to really answer this. So if you said something different, but you gave me a really convincing explanation that just fits the angle you're looking at this in, I would accept that as a full answer for, say, if this was ever a quiz or an exam question. But let's visualize it like this. Let's suppose we have a graph that goes like this, average salary, or excuse me, average work experience going one way. And then for the vertical axis, we can say average annual salary. I don't have specific numbers on the axes because, again, we have no data. This is just a one sentence statement. I don't even know if that's a complete sentence at all. But we could probably imagine if this was N equals 500 companies in USA, hopefully randomly selected companies, the graph would probably look something like this. It'd be a scatter plot with lots of dots everywhere, probably quite a bit of outliers as well, as we had determined. But probably if we were to put a line through the data, we would see something like this. So let's write out a statement. The variables are positively correlated. Now we have to explain that we can say because as a person accumulates more and more work experience, we're thinking, say, the work experience here, work experience or skills. I'll just keep that as work experience. Their salary tends to increase. Not as a rule, sadly, would say if they're working for the right company, they're probably going to be supported well. And there are plenty of exceptions to that in the USA economy. For recently, in think 2025, a well-known, well-respected company, Boeing, had to appear in front of a Senate committee being grilled on why were their top engineers getting between 1% and 0% raises for well over 10 years. And the top corporate executives had to explain why no one was ever getting a raise. Even though people were working there for over 10 years, no one had been getting a raise for a very long time at Boeing, even though they were highly trained engineers. So that's unfortunate. But here we're thinking that was one exceptional case, maybe not as exceptional as we'd like it to be in the USA. But as a generic rule, work experience does tend to increase salaries. So again, that's a tricky part A there. Any last questions or thoughts that folks would like to add to this one? Okay, and in hindsight, I probably should have swapped around part A and part B. Part B is not as bad, so let's work through this one and see how it goes. First thing we want to do is just take the variables and then assign a unit to them to prove that it can be put on a scatter plot and maybe visualize that as we go. So we have vehicle speed on Interstate 15. That looks like one variable. And the travel time between Idaho Falls and Pocatello. So we can put down vehicle speed. This time, the name of the variable didn't necessarily give away the unit. It didn't say what it was, like on this one, where years has a unit in years. For vehicle speed, the unit could be, if you're feeling fancy, kilometers per hour, meters per second, but traveling on I-15, you're probably thinking miles per hour is the normal unit for speed. So we'll say unit is miles per hour, or the common abbreviation MPH would be a fine way to answer it. Next is travel time between Idaho Falls and Pocatello. So let's say travel time. That's the next quantitative variable, which means it also has a unit, but it's a time unit. So if you gave me something like seconds, I mean, that works. We could measure travel time in seconds. That absolutely fits the problem. But if we were taking speed in miles per hour, probably we're thinking of time in hours as well to keep the units compatible. So probably the best answer going off miles per hour is unit is hours. So certainly your speed on I-15 is highly correlated with your travel time. What would you all say this one should be? Is this a positive correlation or a negative correlation?
Negative correlation because as the vehicle speed increases, the travel time goes down.
Yeah, absolutely. So let's put it down just as you said it. I think that's a great answer. Negatively correlated as the vehicle speed goes up, the travel time goes down. So with that assessment, we're thinking of a graph that essentially goes like this. This is speed, miles per hour. This is travel time in hours. And as speed goes up, we're first saying on the low end here, a small amount of speed. But as the speed goes up, travel time should go down. So the graph should look more like this. Again, if we're measuring a random selection of drivers on I-15 on maybe randomly selected days of the week, something like that, this is really a scatter plot. So the scatter plot might look something more along these lines. Some of the vehicles going faster or slower mean the correlation may not be perfect, but the cloud of points would have a generally downward direction for negatively correlated. Well, any last questions or thoughts, folks, on getting through either one of these? Okay, again, they're pretty tricky questions. When you see them on the MyLab homework set, it's some random scenarios kind of like these, and it's not always easy to kind of determine if there should be correlated or not, or what the direction can be is really tricky as well. If you visualize a graph like this, it really helps a lot. And one good thought that goes along with that is the order they give the variables is pretty important as well. So whenever we are thinking of these variables, the first variable is the one on the horizontal axis. Sometimes that first variable is called the explanatory variable, and the second variable given is sometimes thought as the response variable. We're thinking that annual salary can be explained by average work experience, and we're thinking that travel time can be explained by the speed that the car is going in the same as well. Well, that's the conclusion on that one. Next example we're going to take a look into is going back into the causality aspect of the notes. And before we jump into causality, our author has several guidelines when he talks about causality. I'm not going to directly write an exam or quiz question on all these 6 bullet points, but or this is just a guide to think a little bit more. What are we trying to say when we say cause and effect? How can we actually come up with a set of rules or guidelines to determining that variables are connected causally, that one variable causes another? Well, as far as the guideline goes, it says, if you suspect that a particular variable, the suspected cause, is causing some effect, then here are the guidelines to determine that. And a great way to think about this is to go way back in time, back when they're trying to establish whether smoking causes cancer. It's just a great set of variables to think about in terms of cause and effect. When they were looking into whether smoking causes cancer, this was not easy for them to establish, and it took mountains of scientific data, research to really show the link between cause and effect. It starts off with the first guideline. Look for situations in which the effect is correlated with the suspected cause, even while other factors vary. So when they're trying to look for cause and effect between smoking and cancer, they were looking for people in different kinds of job environments. People who might have, say, worked at blue-collar jobs versus people who worked white-collar jobs. They determined how many people got lung cancer to see if it was maybe a job aspect in some cases. In some cases, it might have been. Some jobs, say working in a coal mine, for an extreme example, causes some big problems. The next thing to look for to establish cause and effect is among groups that differ only in the presence or absence of the suspected cause, smoking causing lung cancer, check that the effect is similarly present or absent. In other words, they had to look at groups that of people who did smoke, look at groups of people who did not smoke, and then look at the rates of incidence of lung cancer among both of the groups. If, for example, for some reason, people who did not smoke were getting lung cancer at the same rates, that would have caused big problems in establishing cause and effect between smoking and lung cancer. Well, there's several more guidelines, but any questions so far? Okay, well, still thinking of cause and effect between smoking causing lung cancer, the next thing that you have to do for guidelines for causality is look for evidence that larger amounts of the suspected cause produce larger amounts of the effect. And that's in fact historically what people did. They didn't just say, did you smoke or not, and determine if the incidence of lung cancer. They looked at how much people smoked. People who tend to smoke very little or only exposed to secondhand smoke had smaller amounts of effect. They had lung cancer at smaller rates, less incidence of lung cancer. Whereas people who were more on the other end of the chain smoking had lung cancer at much higher rates. So that made the link between cause and effect even stronger when they got there. But that was just a link. The cigarette producing companies were able to correctly argue in court that there's a relationship between the variables. Sure, higher incidence of smoking seems to be related to higher incidences of cancer, but to really prove that, you have to go much further, much beyond that, because it could have been, and they successfully argued this in court, it could have been a coincidence in the data, or there could be some other variable that's not being accounted for that's causing the lung cancer, not smoking, surely. The people who are manufacturing the cigarettes were discussing. So these guidelines are helpful, but they're not enough to prove causality. That takes a gigantic amount of work. So that takes us to guideline 4. We had to look if the effect might be produced by other potential causes. Is there some other lurking variable causing lung cancer that could be part of what's going on? And again, there were plenty of causes for lung cancer. People were exposed to asbestos at higher rates. There were literal coal mines back in the day, if you're going, say, 70s or earlier. But when they looked into smoking, smoking seemed to still account for a major effect in the incidence of lung cancer. So for guideline 4, we have to try to account for every lurking variable possible, but that's still not good enough. We mentioned much earlier in chapter 5, talking about statistics, that if you really want to establish cause and effect, really what you have to do is a design and control experiment. So that's guideline 5. If possible, test the suspected cause, smoking causes cancer, with an experiment. Experimental design can establish cause and effect. But here's the trouble. There's ethic boards when it comes to experimental design. You really can't take, and this is true for back in the day, you can't take, say, 200 people and say, out of 200 people who do not smoke at all, we're going to randomly assign 100 of you to smoke 12 packs of cigarettes per week, and randomly assign the other 100 of you to not smoke whatsoever. And then at the end of, say, 50 years, we'll track the incidence of lung cancer. If that experiment could have been performed, it would have been extremely informative. It would have taken a lot of years and decades for it to come to its conclusion, but it just isn't ethical to subject humans to experiments where we suspect that the treatment, smoking, is harmful. So they couldn't do this at all when they're trying to establish cause and effect between cigarettes and lung cancer. Eventually, what happened was biology progressed to a point where guideline 6 was possible. Guideline 6 says, try to determine the physical mechanism by which the suspected cause produces an effect. And a biology class talks a little bit about this. Biologists looking into cell biology were able to look into human cells of the lung, and they found the specific mechanism in cell biology, some kind of tumor necrosis factor that gets destroyed when certain parts of the cigarette binds to that part of the cell, and allows for the cell to become tumorous and then cancerous. So they were able to finally show that how the whole process works. Once they were able to establish this, it went well beyond statistics. That was cell biology, but they established cause and effect between the two variables. So if you can't do an experiment, you have to show exactly how the cause and effect works. So again, that's our 6 guidelines. And the purpose of these is just to think a little bit more about cause and effect, how it's established, and the rules in the next example. Any questions whatsoever about those 6 guidelines? Okay, well, with everything we thought about with cause and effect so far, keep in mind that the major danger here is anytime you see something that's correlated, even if we say the correlation is weak or the correlation is strong, we read out the variables and we say there's a correlation between resting heart rate and VO2 max. As resting heart rate goes up, VO2 max tends to go down. When we say that and we disseminate that information to anyone, say in the news, in the media, any kind of form, it's easy to get mixed up and think we said cause and effect when we really didn't. That wasn't the intention on this one. We're just seeing if there's a relationship between the variables at all. There's a lot of mechanisms that can affect VO2 max, and resting heart rate, even if it does cause a change, that wasn't what this study was trying to convey. So thinking about cause and effect kind of protects us from making wrong conclusions when we see these kind of problems. And write out these conclusions here. There's a weak association between resting heart rate and VO2 max, but we don't mean one is causing the other. And while we keep that in mind, even though this scatter plot is kind of silly in a certain sense, keep in mind this could have been any other set of data, and it's easy to get mixed up and accidentally think cause and effect is working in the background. So here's another scatter plot. This time the dots are orange because we're talking about fires, so it's like a good design choice. The scatter plot shows the number of firefighters responding to a fire alarm versus the total estimated dollar amount of property damages caused by the fire. And this is a true correlation that we see. As the number of firefighters responding goes up, in the 20s all the way up into the hundreds, the estimated property damage in thousands of dollars also goes up. So if we were to describe the correlation and the strength, we can say, well, I wouldn't call this one strong. We might call it weak, or even moderate would be fine. But there is I'll go for a weak on this one. Weak correlation between number of firefighters and property damage. We see from the correlation, the graph tends to go upwards. As firefighters responding increases, so does the property damage. So we'll say here, the correlation is positive. So that's our first part there. Part B is pretty similar from what we've been doing on our other scatter plot problems. What conclusions can be drawn from the scatter plot? Here we need to be really careful when we write out that conclusion. If the correlation is positive, then we can say, as the number of firefighters increases, so going left to right on that horizontal variable, the estimated property damage, we don't want to say anything that could imply cause and effect whatsoever. So we might just say this way, the estimated property damage tends to increase. There's a lot of other ways you might say it as well that might be safer. Saying tends to increase, again, if we just took a random person in USA, they might infer that we're trying to say cause and effect just based on that one word right there. So it's a dangerous conclusion, even though correct on paper to write. If you want to be even safer, you might say number of firefighters is associated with higher amounts of property damage. Or let me say that a little bit better. Higher numbers of firefighters responding, so I want to mention a direction here. The higher the number of firefighters responding is associated with or is related to higher amounts of property damage estimated. So saying it that way takes the tends to increase out of the problem and might help you to less accidentally convey to the random person you meant cause and effect. Well, any questions at all, folks, with parts A or parts B? Okay, well, as far as part C goes, oh, sorry, the rest of the chat just got in. Echo says, it's hard not to think cause and effect when you use emotional language. Yeah, I agree with that as well. And it's hard to avoid the emotional language here when we're talking about fires, which is if you've been in a fire, that's already a big deal there. And when we're talking about estimated property damage at the same time, it becomes loaded as well, especially if you've ever had, say, a home claim to a wildfire or other natural disaster. So yeah, I agree. Once there's emotional language in the problem itself, cause and effect becomes almost sticky. It's hard to get away with that. I agree with that comment there. Other questions or comments so far? Okay, well, here's our chart. And again, part C seems kind of silly. Is there a cause and effect relationship between the two variables? We would probably say definitely not. We know firefighters do not cause fires. Usually, there are a couple extremely rare cases of really notorious arsonists that were in fact firefighters, but we mean in general. We don't mean every single firefighter. So when we look into this, we don't really mean cause and effect, even though, again, there are a couple notorious arsonists that happen to be firefighters. We'll say no. There is no cause and effect. So what is going on in the data? The variables tend to move together, but there's a third variable that explains the direction of both of them. Let me move this on to the next page just so that we can not cram this in. Sometimes when variables are associated like this, the lurking variable, some other accounted for variable, is what's causing the relationship. And here the lurking variable might just be the severity of the fire itself is what's tying both of these together. So we can say here, for the explain part, there is a lurking variable the severity of the fire. And the severity of the fire, there's probably a good ways to measure this. If we're thinking wildfires, it could be active acres that the thing is burning on, for example. So as the severity of the fire becomes more extreme, more firefighters must respond, and more property damage occurs. It's really the severity of the fire that's actually causing the property damage in the first place, not the numbers of firefighters responding. They're here to take care of the fire itself. Well, that's our complete discussion on causality. Any last questions or thoughts, folks, on wrapping up this question here? Okay, well, as far as a problem like this might go, say in an exam setting, either exam 3 or the final exam, there'll be some questions along the lines of how strong is the correlation? So you'll have to assess, is this strong or weak? I'm going to try to not put, say, middle of the road problems. This is basic picture for a weak association, and this will be a basic picture for something that's more strong. Since we never calculated the actual correlation or gave a rule of thumb for that statistic, we'll just be doing it visually using these set of notes as our examples. You'll be asked to assess what conclusions can be drawn for the scatter plot. So pretty much what we did on our part B for a lot of the examples. And there could be a question about the cause and effect relationship. When you go to give an explanation, that's pretty much what you're looking for. It might be yes, that the variables do affect each other as a cause and effect. And if it's no, your explanation is look for something that's lurking that can explain the two variables. And for a question like that one, I'll try to make it pretty clear and easy to spot what the lurking variable might be. Not one of those tricky ones where it could be kind of hard to suss out what the actual variable could be that's moving both of them. But we did it, folks. That's the conclusion of our entire chapter 5 on statistics. Really just scratching the surface of statistics, thinking about the variables, statistical design, and descriptive statistics with graphs. Echo says, it reminds me of a correlation study. I showed that shark attacks increased at ice cream sales increased. Yeah, that's a pretty good one. I like that. I'm not sure if I've heard of that one, but that kind of makes sense. Let's put this one down on paper as well, because that's a great additional way to think about a lurking variable. So from a comment in class, this is a great response here. If we look into the variable of shark attacks, maybe that's going to be, say, the property damage, and ice cream sales. The number of shark attacks increased as ice cream sales increase. Ice cream sales would go on this variable. That's the same kind of variable here. Doesn't mean we want to ban ice cream sales, right? Or here, it doesn't mean we want to limit firefighters responding. But as Echo said, the weather, and this one is the lurking variable. People just tend to be in the water more and buy ice cream more at the same time when the weather is nicer. Much like in this problem, as the severity of the fire is more extreme, more firefighters respond and property damage gets more and more out of control. So yeah, that's a great example. Thanks for mentioning that one. Other questions or thoughts? Okay, well, let's close this section. And for now, what we're going to start next is our chapter 8 on exponential growth, exponential decay, and modeling. So let's start off that new chapter, which will be kind of exciting. We're changing gears in a big way. Chapter 5 was challenging because it had a lot to do with context. And chapter 8 kind of goes a little bit more back to what we've been doing since chapter 2. There'll be some context, but we're not just, say, analyzing things, determining if a sample is a cluster sample versus a stratified sample and so on. We'll be doing some computations much like we've been doing at the start of the course. So chapter 8 has a kind of a interesting title, Exponential Astonishment. And for the first unit, kind of a warm up to this section, we're going to look into linear growth versus more on target with the chapter, exponential growth. So we have two basic growth patterns that our author is going to prime us for. Linear growth we've seen in various contexts already throughout this course. So we'll look into a couple examples once again. Linear growth occurs when a quantity grows by the same absolute amount in each unit of time. So the same absolute amount growing by, say, $5, say, for a raise per year would be linear growth. But sometimes when we're thinking about raises for a company that actually gives raises, not Boeing, raises aren't always by, say, $5 every year. Sometimes they're by a percentage, maybe 2% if they're stingy, more like 5% if they're trying to beat inflation, keep your standard of living about the same. So we'll say exponential growth occurs when you're not getting raises by, say, $5 per year, but say 5% per year. Exponential growth occurs when a quantity grows by the same relative amount, or sometimes thought of as just strictly the same percent in each unit of time. Well, that's our two different kinds of growths. Example one, our major job is examples 1 through 4, is just to determine what kind of growth factor we're looking at, and then analyze the growth in the second question. But any questions so far, folks, with the two growth patterns? Okay, so let's maybe add those comments here for the notes, just as a quick mental model. We were talking about raises recently in one of our scatter plots, so it's fresh in our mind. So if we say a raise by $5 per year, then that is linear. We're thinking $5 an hour. I should specify, give it a rate, or $5 for the entire years of work is a pretty small raise. So $5 per hour. If we say we're giving a raise by 5% per hour, then this would be, let's make this parallel per year. This is exponential. So those are the two different kinds of growths that could occur. And here's our first example to start thinking about these two kinds. So for this example, it talked about lo-fi music, and I realized I have no idea what that really actually is. So here's the quick definition to make the context a little bit more fleshed out. It says lo-fi is short for low fidelity, and this is a music genre and production aesthetic that is characterized by intentionally incorporating imperfections. So it's warm, nostalgic analog sound, including things like vinyl cracking, tape hiss, and other imperfections, warped pitched, and so on. And some listeners, for some people, the mellow beats, warm analog sounds create a relaxed ambience for studying. So if you like music for studying, give that a try. You might like it or hate it. I think people are pretty divided on lo-fi music. But nonetheless, that takes us to the major part of the problem. It says a student creates a lo-fi music playlist for studying, and the channel starts gaining traction online. So we're talking about growth. When it says gaining traction, that channel is growing listeners. The number of daily listeners tuning into the playlist is increasing on average by 45 people per week. So that's our increase. And what would you all say for this one? Would this mean it's growing linearly, or is it growing exponentially?
Exponentially.
It turns out this one is not an exponential growth. And the reason for it is when it says it's increasing on average by 45 per week, we mean it's going to be the same 45 every single week, week after week after week. And so this one is the one that turns out to be linear growth this time. If they said something different, if they said, say, 4.5% of its size of people per week, I guess that's a complete sentence. If it was growing that way, Then it's changing by a relative amount or a percentage amount is usually how I would say it every single week. And that's what would make it exponential in this context.
Okay, so when they say on average, they're gonna, so if it says increasing on average by 45 per week, it's gonna be using that 45 every single time as the average number instead of because in my head I was kind of thinking about 45 every week.
Yeah, that's essentially what they're saying, whether you say about 45 or on average 45 every week. What they're meaning is maybe they started this weeks ago and they looked into 10 weeks, looked at how much it increased by every week over those 10 weeks. And on average, it's 45 per week and looking stable. So that means in the next week, it might go up 30, it might go up 52, but this is just going to be their prediction. They're expecting it to go up by about that amount, like you said. And I agree, the word average thrown in there kind of muddies the waters right here. We're saying the same amount, and now we're saying here, on average, it's going to go up by that same amount. But does that make sense with the question there so far?
Yeah, thank you.
Yeah, you bet. And yeah, I agree. Reading this again and looking at the definition here, that word on average definitely kind of muddies the water on making that assessment. But still, we'll go for this as our gold standard for exponential growth. If it says on average by 4.5% a week, or if we lost the word altogether, we'll think of this as being linear growth. And this moment it turns into something like that, we'll think of it as exponential, whether there's average or not in front of it. I guess this problem is just being more honest that they don't know if it's exactly going up 45, but that's their educated guess on historical data. So here we'll assess this by saying linear, the number of listeners increases by an absolute amount of 45 listeners per week. And let's mention that that's not exact, that's just on average. So we have linear growth on this one. And now that we know the growth pattern, we can make a prediction on part B. This is assuming this average is highly accurate or maybe even exact. We assume that it's going to go up by exactly 45 listeners per week. And if it has 850 listeners today, we can make the prediction to how big the number of listeners for this playlist would be in 4 weeks' time. And really, it's just going back to chapter 2, doing a little bit more unit analysis like we did back in that chapter. We can take the base amount we have currently, 850 listeners, then if we're looking into linear growth, what we'll do here is add the growth rate to this, but only if the growth pattern is linear. For exponential, we'll do something different. We would have to multiply instead. So what we're adding is the growth rate, 45 listeners per week, the prediction is going to be in 4 weeks' time, so we multiply that by 4 weeks. So that's our time frame in the assessment. Then just grab a calculator, observe that the unit week and week will cancel here. So the whole value is going to be in just in terms of listeners. So take 850 plus 45 times 4. And we're up to 1,030 listeners. Well, that's our analysis for the linear growth version. Any last questions or thoughts, folks, getting through example 1? Okay, again, sometimes these can be a little bit tricky to determine what the growth pattern should be. So let's see what's going on for example 2. I included in red here, I forgot once again to put information on rounding, so that's what the red part is about. That's been the tricky thing about writing these notes all semester. Sorry about that distraction there. This one has a really short context. It just says, a gardener plants a small patch of milkweed to attract pollinating insects, which you have to wonder about the judgment there. It literally says weed in the name, but this is what they did. It says next, because the plant self-seeds aggressively, the total number of milkweed plants in the garden increases at a rate of 18% per year. Well, based off this part right here, what would you all say is the growth pattern this time? Does this look linear or would this look exponential?
Exponential this time.
Yeah, I agree. And one way that the exponential is probably a really big dead giveaway is a percentage was given, right? In other words, if you have linear growth, you have to say what the actual absolute amount, whether it's number of listeners, dollars per hour, that something is growing by. But if all you're given is a percentage this time, in that case, we're looking into exponential growth. So rate of 18% per year is telling us the growth rate is exponential because the amount changes by the same percentage every year. And that wouldn't happen with the $5 raise. The first time you get a $5 raise, say you're working at $15 an hour, your first $5 an hour raise is humongous. But then your next $5 an hour raise is not as substantial in terms of the percent raise you're getting. And then year after year after year, the percent raise you're actually getting just gets smaller and smaller and smaller. But if you're getting a raise by 5% every single year, the actual amount you're getting a raise by is just going up and up and up every single year. So exponential growth definitely has a different kind of feel for what that's going to look like on paper on any kind of context, whether it's milkweeds growing or raises being given year after year. And now that we know that the growth pattern is exponential, here, when we go to make a prediction, we have to work a little bit differently. For linear growth, we added on a value. But for exponential growth, we have to multiply. So here's what the pattern is going to look like for the exponential growth portion. We start with the 30 milkweed plants, just like part B here, started with the 850 listeners. So take 30 milkweed, and this is how much we have currently in the garden. We want to know how many there are going to be in 3 years, and we can do this kind of computation. Year 1, take the 30 milkweed already existing, and it's growing at a rate of 18% per year. So we can say, well, that's a rate R. If we write as a decimal, that's 0.18. And we multiply this by 1 plus 0.18. In other words, we're multiplying by 1.18 or 118% if something's growing at a rate of 18%. This might give you a sense of deja vu. We've done something like this very similarly before. If we want to know year 2, how many milkweed will be in the garden in year 2, we would just take the amount we have in year one and then multiply it by this factor again. But that would mean take 30 milkweed, multiply it by 1 plus 0.18, now raised to power 2. And then the pattern just keeps on going. If we want to know the amount of milkweed in the garden in year 3, take 30 milkweed, the starting amount, take 1 plus the growth rate, 18% as a decimal, 0.18, but now raise that to a power 3, and that would give us an answer. And again, here's the tie-in. We did something pretty much exactly the same in power of compounding. Here we had a principal of $8,000, a growth rate of 2.5%, which is much smaller than the 18%. That was the APR. Instead of saying 3 years, we did 6 years. But all we did was, if we want to find the total amount, we took 8,000, the base amount, plus 8,000 times the growth rate, got an amount and did it all over again. But we noticed as we went across all the years, you could just write it in this format. Take an amount, multiply it by a group, 1 plus the interest rate as a decimal. And if you put all these together, when we worked out this little demonstration, we found this format is actually what really holds. If you take the starting amount, 8,000, multiply it by the interest rate, raised to the power of the number of years, you get the ending amount. And that's exactly what we're doing here. We're taking a starting amount, 30 milkweed. We're using the interest rate here. Well, growth rate, since it's not money this time, we don't call it an interest rate, APR. Raise it to a power of the number of years. And just like it was back in here, for this example, compounding once a year, this is what exponential growth looks like, whether it's milkweed in the garden or money in a bank account. I think this was money someone was owing someone else, rather. That's a pretty interesting tie-in. What we're doing in this section is very similar to what we did in the past. So if we have exponential growth, this is how we find out the growth pattern. We can just jump right to year 3, get a value out. To the nearest whole year, this will come out as, take the 30 times 1 plus growth rate as a decimal, so 0.18. All we do is we take the decimal point here, move it back 2 spots, so it's a 0.18. Raise it to the number of years in the question, whether it's 30 years or 3 years, put in that value. And to the nearest whole number of milkweed, there'd be 49 of them altogether. So 49 milkweed. And if this pattern were to continue, say we're talking about 15 years down the line, we're up to nearly 360 milkweed. At some point, this exponential pattern kind of breaks down because this might take up more area than is actually available in this garden. So exponential growth might be accurate in the short term, but in the long term, it's probably going to break down. For example, we can't worry about what happens in 40 years. That's 22,511 plants. Probably not enough area in the garden to cover all that, and that's a pretty long time frame as well. Well, these are the 2 major kind of problems we'll be taking a look into when we finish out these notes. On Wednesday's class, we'll do a couple more problems where it won't be so easy to spot right away if it's linear or exponential growth. But we'll practice a couple more problems and then tie back again another financial problem where the thing growing is money. Any last questions or comments at all, folks, before we call it a night today? Okay, well, have a great night, everyone. On Wednesday's class, we'll work through these notes, but you will possibly finish it and start the next unit as well. But have a great night. I'll see you all Wednesday.